The lecture is being recorded now. Can someone please confirm if you can hear me? All right, I got a confirmation. Thank you very much. So this is lecture number 18, and today we'll start a new topic, which is titled Deformation and Motion. Okay, so till now we have learned about the background mathematics, which is useful for quantifying the physics in continuum mechanics. And the second one, we studied about stresses, which is talking about the internal stresses that are developed at different points inside the body as we load the body externally because of some external stress field. And we will call it the stress field for the stresses inside the body, because we won't, I mean, although we discussed about stresses at a given point P inside the body, but we'll want to know the stress field, which is stress at all the points inside the material body. Only then we can find the deformation and the motion of the body as a whole. Okay, so remember that in quantum mechanics, the aim of this course is to, I mean, we said it's mechanics. That means that we'll want to know the movement of the body, but some external forces acting on the body. So in continuum mechanics, we talk about the internal deformation of the body. So if you have an internal stress at a given point inside the body, that leads to some sort of deformation or some sort of motion of different points in the body, which ultimately results in the deformation of the body as a whole. It can also result in the in the motion of the body as a whole, which is the displacement of the body, that is translation and rotation. So that's a rigid body motion of the body. All right. So once we learn about stresses, which are equivalent to forces in classical mechanics, and deformation and motion, which is equivalent to the kinematics, then we can link the two. So we can link the two using laws of motion, so that we can understand if we apply a certain amount of stress, then what sort of deformation does that stress cause. So that will be the topic of discussion after this chapter. Any questions about the previous lectures before we start? All right. So in today's lecture, we'll be talking about first the configuration. That is, what is the meaning of when we say a body goes through different configurations. So we'll define the terms. Then we'll also define the material and spatial coordinates. So to be able to define motion, we need to have some sort of coordinate system to define that motion. So there's two two coordinate systems. One's called the material coordinate system, the other is called the spatial coordinate system. Then we'll talk about the Lagrangian and the Eulerian description of motion. So we'll again have two coordinate systems. One we'll call Lagrangian, the other we'll call Eulerian. And then finally, we'll end the lecture with talking about displacement field, which is very useful when understanding the motion in a body. Okay, just a couple of announcements. So till now, I've got only 30 responses on Moodle. So that this was a feedback form for you to tell me if you have a decent enough connection to access the material for the course in quantum mechanics. I only got 30 responses, so I am assuming that the others don't even have access to the internet. Now, I know that may not be completely true. It's just that they haven't accessed Moodle till now, or they just don't feel like responding. But we'll keep continuing with the same mode of teaching that we're going through. So we are going through online discussions over Zoom. Then the discussion or the lecture is being recorded and uploaded over Moodle as well as YouTube. So in case the students cannot access these video lectures, they're always free to come back whenever they do after this COVID-19 protocols over, and they can access these video lectures so that I don't have to teach them again in person. So everybody will have the access to the same amount of material. We'll just make sure that everybody does have enough time to go through this material. But I suggest that if you can attend the meetings, please do that, because that gives you the opportunity to ask questions during the meeting, which ultimately helps you and everyone else. Again, the PDF of the lecture notes is available on Moodle along with the book and the reading assignments. So you can always go through them. Now, problem set number 4 will get uploaded on Moodle by tomorrow. And solutions to problem set 3 will also be uploaded tomorrow. So when talking about the deformation and motion, we'll talk about our body. So let's assume that we're dealing with a solid body for this discussion. So the solid body has a shape, a volume it occupies. So let's draw an arbitrary shape and call that our body that we're interested in. And we have a coordinate system that we'll be using to locate different points inside the body. So let's say I have a point A. That's a material point, as we call it. So every body is made up of material points. And remember, we're talking about continuum mechanics here. So it's a continuous collection of points which make a body. So point A is just some arbitrary point inside the body, which will have a coordinate, a position coordinate, which we'll denote by capital X A. It appears that there is a lot of lag between what I'm writing and what you are seeing. So I'll try to go a bit slow so that it doesn't confuse you. And let's say we have another point, which is point B, and then the position coordinate of point B will denote as, in this case, XP. Okay, similarly, whatever point you have, you can define a position coordinate for that point. Now, the X that I'm writing is a capital X. So this capital X will be called the reference coordinate system. So we have infinite number of points inside the body. So to be able to locate the configuration or the position of different points inside the body, we can define a function or a mapping. So this function we'll call kappa. Well, it's not clear. I'll write that clearly. So this is kappa. So kappa takes the ID of the material point. Now ID is just an identification. So we can identify the points using alphabets, numbers, whatever you want. Okay, it's an identification of a point. And this function is a vector function. That is, it returns a vector, which is the position vector of the point capital X. So capital X without the vector arrow on the top denotes the identification of the material point, which can be, which in our case, we're using alphabets for that, capital alphabets. And then this kappa function, it takes the ID and returns the position vector of the point X. Okay, so once we have this kappa function available to us, it gives us a configuration. Okay, so if I know, I have a list of all the points that make the body, and I have a list of, I have a kappa function. So I basically have the position of each and every point in the configuration. So as I change my configuration, that is, let's say you take the body and deform it, then the position that different points occupy in space will also change. And these positions will then correspond to a new function, which we can call as kappa 2. Okay. So we just have to understand the ideas here. That kappa function helps us define a configuration of the body. Okay, then we can also have an inverse of kappa. So kappa inverse basically gives us, so given the position in space, kappa inverse will tell us which point lies on that given position in space. Again, as we said, that the configuration can change through rigid body motion, which is a sum of displacement as well as rotation, and it can also change through deformation of the body, which is change in shape and size. Okay. All right. Next, we have to talk about motion. So when a body moves, that's basically taking different snapshots of the body in time on the time axis. So what happens is that the body goes through different configurations. So for every time, as the time proceeds, we have a new configuration that the body takes. Okay. So we can now define another function which has more information than the previous function. So we'll say that let our x, which is the position coordinate, be a function of, so kappa be a function of the ID as well as time. So that is to say, you give me the identification of the point as well as the time, and then I'll tell you where exactly in the reference coordinate system the particle is. So I'll tell you the location of the particle given the particle ID and time. Okay, so this kappa function now contains more information. It contains information about the motion. So if I give you this kappa function, then you have all the information available to find the how the body moves in time space, the time coordinate space, or how the body changes configuration with time. Okay, similarly, I can define a kappa inverse so that if you give me the position and time, I will tell you which point lies at that position. Okay, so it's the inverse of the kappa function. Okay. So now there is another term we'll define, which we'll call the reference configuration. Okay, so what this means is that, I mean, now that we're talking about motion of the body in time, then we'll have multiple configurations to compare with. So I'll have, let's say, for instance, we have the body at t equal to 0, and then the body changes shape, moves, etc. And now we have the body which has completely moved and changed shape at some t equal to t1. So point A initially was here, and now the point A has moved here. So the point A has displaced. So to talk about this displacement of the point A, we'll have to define a reference configuration in reference to which we'll define the displacements. So it's completely our choice to define the reference configuration, and the most common choice is the initial configuration. That is, as I took in this particular case, I took t equal to 0 as the reference, which is again the most common choice. But again, it's a choice of the user. So you can always decide what particular configuration you want to have as a reference configuration. All right, so as I said that mostly it's the initial configuration which is considered as the reference configuration, but again, it's your choice. In fact, you can think of a hypothetical configuration, that is a configuration which the body never assumes realistically, and you can call that as a reference. It's completely your choice. Okay, so you can think of hypothetical distribution of the points in the body, and you can call that as a reference configuration, but that's just complicating matters, which may be useful in certain situations, but in our discussions in the future, we'll use the initial configuration as the reference configuration unless I state otherwise. And then we have something called the current configuration. So this configuration is the configuration which the body assumes at time t, which in this case, in the figure that I drawn, I called t1. So at any time t, the configuration the body has called the current configuration. Okay. It's also very common to call the reference configuration as the undeformed configuration. And the current one is called the deformed configuration. Okay, again, these are just terms. So we're defining terms so that in the future when we use them, you can refer to these notes and understand what exactly they mean. These are simply definitions. So next, we'll talk about the material and spatial coordinates. So this topic is one of the most confusing topics in this course. So please, if you have any questions, feel free to stop me and ask questions, because in classroom lectures with Blackboard and Chalk, I usually spend a lot of time discussing these things. But on the online discussion system, I might tend to go a bit fast. So again, it's simply a coordinate system. So please note that I'm using capital X in this case. So that's for the material coordinates. So what you may notice here is that the unit vectors, unlike E1, E2, and E3, I'm using capital I1, capital I2, and capital I3. Okay, so that's a common way to write unit vectors in the material coordinates. So remember that you have a reference coordinate system, or the undeformed coordinate system, and then you have the current coordinate system, which is the current you have the current configuration where the body is at any time t. So we took the reference as the initial one, where we said that which is at t equal to 0. So that's the shape of the body, that's the configuration of the body at t equal to 0. So at t equal to 0, the body has, every point has a certain position occupied in space, so that we can use a function kappa or a function phi in this case to denote the configuration of the body. So what we'll do is we'll write this capital X, which is the position, as a function of x, where x is the particle ID. And phi is, instead of kappa, I'm using phi here, because the book uses phi in this subtopic. That's the only, it's the same as what you had kappa earlier. Okay, now at a later configuration, at a later time, sorry, the body may move. So let's go to the next page. Okay, so that top figure is the reference configuration of the body, and the second body that I've drawn is the current configuration of the body, that is at some later time t. So a point P, capital P, in the reference configuration becomes a point small p in the current configuration. So it's the same point except that it's moved in space. So we use a different notation for that. So the position coordinate of capital P is denoted as capital X. Strictly you will call it capital X P, but it's an arbitrary point, so we just use capital X for the position coordinate. But for the small p, which is in the current configuration, you use small x vector. And then we have I1, I2, and I3 as the unit vectors for the reference coordinate system. Now for the current coordinate system, In this case, we are choosing the same axis. So we call it small x1, small x2, and small x3. And then we have E1, E2, and E3. But again, you can choose different axes for the reference and the current coordinate system. Okay, and then you have a displacement, which is from capital P to small p. That's denoted as U. So U denotes the displacement of the body. We'll talk about displacement more in the next few discussions. Now, let's try to understand what's the difference between material and spatial coordinate system. So in the current configuration, where we are using a small x vector to denote the position, and now the point capital P has moved. So it's occupying a different location in space, but but it is the same point. Okay, so think of multiple current configurations. Okay, so I've drawn only one here, but I could have drawn multiple configurations as my time goes along. So I can have a third configuration, I can have a fourth configuration, a fifth one, and so on. Okay, so body configuration is changing as the time proceeds. So what we're seeing is that using the small x coordinate system, I can my small p will move in space, but the capital P is fixed because it is the reference or the initial configuration. Okay, so it always denotes t equal to 0 configuration of the body. So although my small p, the coordinates of the small p are changing with time, but the coordinates of the capital P are fixed because they were defined for a given time, which was t equal to 0. So I can always identify the point P using either the current position it has and the time for which we're talking about, or we can identify the point P using the initial coordinates it had. Okay, so it's very much like we identify people from the place they belong. Okay, so for example, Himachali is you may have someone in the class who you call Himachali. So that that person may not be in Himachal anymore, but it's where that person was born. So you use the ID, you use the coordinates of that person at birth, which is t equal to 0, to identify that person, even though the person has moved out of that position at a later time. Okay, so that's the difference between material coordinates, which are the coordinates of points at t equal to 0, as well as and spatial coordinates, which are the coordinates of points in space at different other times. Okay, so we'll keep if the idea is not clear yet, don't worry, we will reiterate the idea again and again so that it becomes clear to you. Okay, now remember that this capital X was the ID. So let me check what symbol I've been using. So we have to define a new symbol, kappa. So what we're saying is that capital X, small x, which is the spatial coordinate of a given point, is a function of the ID of the point and the time. So that's to say, you tell me the ID, which is, let's say, P, the identification of the point, and the time, and this function will tell you exactly where in space that point is now. Okay, that's small x is a function of capital X and T. Or what I could do was, instead of telling you the ID of the point, I could tell you the location of the point at t equal to 0. So I'm using kappa tilde for the first one because I want to have the different functional forms. So in the second case, what we're saying is that if I tell you the reference coordinate and the time, then you can tell me where exactly in space the point is at that time. So remember that capital X was the coordinate corresponding to some point, material point lying in that coordinate. So as an example, let's take the figure that we have drawn. So if I give you a point, well, let's try to draw a new figure because the current one will not help us too much. So this is the reference configuration of the body, and we have a point here, which is, let's say, 2, 1. So the x coordinate is 2 and y coordinate is 1. This is 2, 1. Now this is the reference coordinate that is at initial coordinates, initial configuration, which is at t equal to 0. Now at a later time, the body now changes configuration and looks like this in the blue color. So that's the blue one is the current configuration. That is at time t equal to t1, let's say. Now this point 2, 1, which was a point, let's say, A in the reference configuration, now in the current configuration, it has moved to point small a, which, I mean, hypothetically, we're just saying this coordinates of point A, small a, are 2.5, 0.5. So we have a displacement from capital A, which was in the reference configuration. Now the body has deformed, the body has moved. So the capital A now has gone to small a, which has different coordinates. So if I actually use my function that I just defined, kappa, in the second form, so I can use, so I can say small x is equal to kappa of capital X, t. So in this case, we have t1. I would want to know where the point is at t1. Capital X in our case is 2, 1. So let me repeat this again. So you have a point 2, 1, which is this point A in the reference configuration. Now this point A in the reference configuration becomes small a in the current configuration. That is, the body moves as a whole, the body deforms, etc. So capital A goes to small a. Now small a has coordinates 2.5, 0.5. So in my kappa function, when I supply the reference coordinates of the point, which is 2, 1, and the time at which my current configuration is existing, then I will get the current coordinates of the point, which is 2.5 comma 0.5. Now the second point to make here is that in the current configuration, my 2 comma 1 is occupied by some point which was at a different location in the reference configuration, which I'll call B. Okay. So at 2 comma 1 in space, we have a small point B in the current configuration, which initially was at capital B in the reference configuration. Okay. So that's the difference between current and I keep using different terms. So material or the reference coordinate systems denote the coordinate system, the coordinates of the points at t equal to 0. And then we have the spatial coordinate system, which denote the point, the coordinates of the point at some later time t in the current configuration. So now what we are seeing is, if I give you some spatial coordinates, let's say in this case 2.5, 0.5, and I give you a time, then you can find exactly what point is lying there. Okay. So what I mean to say is, if I give you some spatial point, some x comma y, and I give you a time, then using a Kappa inverse function, you can tell me exactly what is the ID of the point that's lying there at that time. That if I give you a position in space and a time, you can tell me exactly what point, material point is lying there. Or you can tell me the reference coordinate of that point that's lying there. Okay, so that's the inverse function, which is called the function Kappa inverse. So material coordinates are fixed to the reference configuration of the body, and spatial coordinates denote different current configurations depending on exactly what time you're talking about. So spatial coordinates are fixed to the it's fixed to the room. I mean, the coordinates are fixed in space. It's just that as the body moves along, different points occupy the small x location at different times. But capital X always denotes the reference configuration. So if I go back a slide, go back 2 slides. So in my discussion of spatial coordinates, if I ask you, what is my kappa of capital X comma 0? So my question is that kappa is a function which takes the reference coordinates and the time, and it tells you what the current coordinate of the body is. If I take kappa of capital X comma 0, what will I get? Right, so Saurabh has replied, it's capital X. That's correct. You'll get capital X back because the reference configuration was defined as the initial configuration, that is at t equals 0. Okay. So if I take kappa function at t equals 0 with capital X, I get capital X back. So capital X is defined as the kappa function at t equals 0. So kappa contains this information in the function form. So it's just an identity map from capital X to capital X. Okay, so any questions before we proceed? Because as I said that these ideas are a bit tricky. It takes some time. It's just confuses. I mean, the ideas are very straightforward, except that the terms are a bit confusing. Now, what we commonly start doing is, instead of using the function kappa, now remember that you have been doing this. You have been using y is equal to f of x. You have been doing that, where f is a map or a function, and x is a point in the domain, and y is a point in the range. Now, what you tend to do is you tend to write y is equal to y of x. So it's a very common practice where this y denotes a point in range, whereas this y denotes a function. Okay, so we tend to use the same symbol. So depending on how we are using it, we understand the meaning of that symbol. Okay, and x still is your point in domain. Okay, so we'll use a similar idea. So what we'll do is, instead of using kappa, we'll say x, which is the spatial coordinates of the point, is equal to x, which is now a function of capital X and T. Okay, so this x denotes the spatial coordinates, and the second x denotes the function or a map. All right. Now, for a given particle P, I can use x, which is the spatial coordinates of the particle P, is equal to small x of the reference coordinate of the particle P and the time at which we are having the current configuration for which we are trying to find the spatial coordinates. Okay. So you can use the superscript of the particle ID, and that will give you the particular coordinates of that particle. So for this function small x, you can feed in the reference coordinate of particle P, and you will get the current configuration, the current coordinates of the particle P in the spatial coordinate system. So this basically can be used to find the path of the particle P. So path of P means how particle P moves in space. So that is if at this capital X, so capital X of particle P is constant. It does not change because it's defined at initial configuration, which is t equal to 0. So capital X of particle P is constant. So you feed that into the function, and for different values of your time, you will get different values of the current the spatial coordinates or the current coordinates of particle P, which is small x. So as you change your time, keeping capital XP the same, you will get different values of small xp, which when you join them, you get the path of P. Okay. Now I may be interested in the velocity of point P, so I can always say that the velocity of point P is nothing but d by dt of small x of P, which we can write as del x by, let's use kappa here, it's easier. Okay, so the velocity of particle P is d by dt of small x, because if I go back a slide, then it's small x that contains the information about how things are changing with time, because capital X does not change with time. I can actually write that d by dt of capital X is 0, because capital X is not a function of time. It is always defined at t equal to 0. So d by dt of capital X for any point is 0. It's not a function, mathematically it's not a function of time, but small x is a function of time. Small x tells you how the particle is moving in time. So if I take the derivative of small x, I get the velocity of the particle P in this case. Okay, and then again we can define acceleration as the derivative, time derivative of velocity, which becomes the second derivative of chi with respect to t, where chi is function of x and t. Now we are keeping capital X equal to capital P. Okay, I don't need to write that because it's assumed that you're talking about a particular point P here, but it can be written. So the major confusion comes is velocity the derivative of the spatial coordinate or the material coordinate. It has to be spatial coordinate, because if you take material coordinate, then it will be 0, because material coordinate, as I wrote here, is not a function of time. It's only the spatial coordinate that's a function of time. Let's take an example to understand the things in a slightly better way. So this is the example number. This is example number 421 from book. Okay, so as we said that the motion of the body can be given by this mapping function chi. So a chi will give you how how each and every point in the reference configuration has moved in the later times. Okay, so you feed in different values of capital X, which denote different points in the reference configuration, and small x will give you the path of the different points for different times. Okay, so it will tell you how the point moves. So this mapping chi gives us the information about the motion of a body. So I've written this equation chi, or the mapping function, as the three equations, because x is a vector in a three-dimensional space. So we have three equations here: small x1, small x2, and small x3, written as a function of capital X1, capital X2, and capital X3 and time. So in this particular case, small x1 is equal to capital X1 plus t square capital X2, and so on. Okay, so the motion of a body is given by this system. you have to find the path. So first question is, you have to find the path of a particle which had a reference position of 1, 2, 1. So in at t equal to 0, whatever particle lied at 1, 2, 1, you have to find the path of that particle. Okay. And the second question is, you have to find the velocity and acceleration you have to find the velocity and acceleration of the same particle at t equal to 2 seconds. Okay, because at different times you'll have, so you'll see that as the particle is moving along a path, its velocity and acceleration will keep changing. So you have to find the velocity and acceleration at t equal to 2 seconds. Okay. So let's see how we find the path of the particle. So, so part A, we're interested in the point P, which was at 1, 2, 1 in the reference configuration. So if I go back to the equations, in these equations, I can substitute capital X1 equal to 1, capital X2 equal to 2, and capital X3 equal to 1, because that is the point we're interested in. So if I substitute that, I get my small x1 equals 1 plus 2t squared. Small x2 is 2 plus t squared. Small x3, which was equal to capital X3, is 1. I simply have substituted capital X vector is equal to 1, 2, 1 in the chi function, which is a function denoting the path of the body, or the motion of the body. So if I have the position, the coordinates of the body as a function of time given as this, to find the path, all you have to do is you have to get rid of t here. So we can use equation number 1. We get, well, you can use 2 instead. Okay, so that's what you get. So what that means is, it's, sorry, so the path, so the particles always at x3 equal to 1. That is, the particle moves in a plane which is x3 equal to 1. So what you do is you draw the plane x3 equal to 1. Okay, in this plane, the particle moves in a straight line, which is denoted by x1 minus 2 x2 equals minus 3. Okay, so so the particle is moving in a straight line in the plane x3 equal to 1. Okay, so this gives us the path of the particle P, which was in the reference configuration at 1, 2, 1. Now you have to find the velocity and acceleration of the same particle at t equal to 2 seconds. Now remember that velocity was given by d by dt of the current configuration. Now the current configuration can be written as, I can find the first component of v as d by dt of the first component of x, small x. Now small x was capital X1 plus t square times capital X2. So let me write that here. Small x1 was. So if I differentiate this, the right hand side of this with respect to time, now remember capital X1 is not a function of time. It is at t equal to 0. So that means capital X1, if I take derivative of that with respect to time, it's a 0. So basically I end up getting twice t capital X2. Now capital X2 for this point P was 2. So this becomes 4t. Now t has been given to us as 2 seconds. So that's where we want to define find the velocity. So if I put t equal to 2 seconds, I get 8. Similarly, v2 is d by dt of x2. Sorry. x2 was given as capital X2 plus t square x1. So if I take a derivative of x2, small x2, I get twice t capital X1. If I put t equal to 2 seconds and capital X1 equal to 1, I get 4. And V3 is 0 because my small x3 was simply capital X3. Okay, it does not change with time. So that means the derivative of that is 0. So my V vector for point P is 8, 4, 0. Okay, so you can similarly find the acceleration of point P as d2 by dt2 of x1. So I leave it to you to find that, and you will see that this comes out to be 4, 2, 0. All right. So we'll stop here today. And if there are any questions, I'm happy to answer. Saurabh is saying today's lecture was not viewable in web browsers. All previous lectures were viewable in web browsers. Oh, well, I didn't do anything special today. I'm doing the same thing that I've been doing for the last few days. Can anyone else please confirm if you can see the lecture in a web browser, or are you using the application for this particular Zoom? Does anyone want to comment if you could view the lecture in a web browser? Okay, somebody else has replied it's the same thing. So it's a shame that you could not view it. I mean, could you view it at all, or you just were listening to me? Because Saurabh says not at all, so you could not view the lecture at all. I'm really sorry. Is anyone using an application like an iPad app or a phone app for Zoom? And say if you could access that, because I am recording the lecture through another laptop, which is using a web browser. So I'm using a Windows laptop and with Google Chrome in it, and Google Chrome can actually show the lecture. So I can see the lecture on my laptop screen. Okay, so somebody is using a phone app and it was working properly. Hardik says he could view the lecture in on the laptop. So can you please discuss amongst yourselves and figure out which is working, which method is not working, because I'm not sure it's showing very well on my Windows laptop in Google Chrome app, as well as on my iPad screen, which is what I'm using to write. So any issues, please let me know, and I'll be happy to change the mode. I mean, we can also use Google Meetings, but I think we'll try to stay with Zoom because I've got comfortable with the options by now. But again, I mean, get back to me if you have any problems or any solutions. Okay, any questions about the lecture?